Right on time. Okay. Hello guys, how are you doing? Looking forward for the weekend? Yeah, me too. I don't know why, but probably because I was camping last week. But I want just this week to finish. Okay, so what we're going to do today is we're going to work on the homework and about Wellbore stability. And I don't know how you're doing with the homework, which is due today, but we'll try to save a few minutes for that towards the end. Okay? So the first problem in homework number 7, if I remember correctly, is to find out what are the stresses around a wellbore. Not only at the wall of the wellbore, but also a little bit further away. So you have your computer, and you can, I see many of you have your computer. You can already solve this problem, and you need to plug the numbers in the equations and plot the results. If you don't have a computer right now, I would suggest that you write down the equations and you figure out, you simplify those equations, so then you have to type a little bit less when you use your computer, okay? But let's try to figure out what this problem is about before you plug the numbers in it. So let me split this in two and come back over here. Okay, I think it's good. And let me put this on the side. Let's see. Homework number 7. This is problem 691. And we need to use the equations of Kirsch that I'm going to put them in a little bit on the screen. And we need to calculate sigma r and sigma theta theta. Okay. But the first thing we have to do is to see what are the conditions. So if I have a coordinate system where this is the east, this is the north, and I have a vertical wellbore in here, and over here it says vertical, okay, vertical well. So this is a vertical wellbore, and let's see what else. Diameter is 8 inches. If the diameter is 8 inches, what is going to be the radius? 4 inches, right? Okay. What else? It tells me that the minimum principal stress is striking in east-west direction. So this is going to be SH mean, and therefore if SH mean is in east-west, SH max should be perpendicular to it, because those are principal stresses, and it's going to be coming in direction north-south. I know those values too. SH mean 4500 psi, SH max 6000 psi, and what else? The problem asked me to solve stresses from up to 3 feet of distance from the center, and I have also a pore pressure, which is there is a small typo in there. It should be 3200 psi. So I added space there, but it should be 3200. Okay. And I'm asking you to do this for 2 cases, and also for 2 lines. Okay. let's talk about just one case right now. Let's say that the pressure in the wellbore case number 1 is, in this case, is the same as the pressure, the pore pressure. Okay, before I continue, I forgot to do something. I forgot to tell you how we calculate the pressure in the wellbore and what is the variable that controls pressure in the wellbore. Basically, in the wellbore, there are some variables that we are not going to be able to control. Like, for example, what are the far field stresses, or what is the pore pressure? That's something that's going to be there already. That's something that you cannot control when you are designing a wellbore. Things that you can control is what is the direction of the wellbore, and also what is the pressure inside the wellbore. How do you control the pressure inside the wellbore? With a mud weight, right? And the pressure in the wellbore basically is going to be the density of the mud times gravity times true vertical depth. And this is inside the wellbore. Inside the wellbore, you're going to have a hydrostatic head that connects the top of the wellbore to the bottom. In this case, we're assuming this is hydrostatic. And if you have some other tools like pressure control, or if you have a non-zero pressure on the drilling rig, then you will have to add that. And if you have fluid flow through the annulus and if you're drilling, there are going to be a few more viscous losses that you're going to have to consider. But you're going to see that in drilling. Here I like to keep it simple and to say that the pressure in the wellbore is just going to be the density of the mud, that's something that you can control, times G times the true vertical depth. And remember, it's not just depth, it's not measured depth, it's true vertical depth, because that's a hydrostatic head. It's the same thing as with pore pressure or vertical stress. Okay, so I come back over here, and in this problem number 1, what I'm asking you is to tell me what are the values of sigma RR and sigma theta theta for theta equal to 0. What does theta equal to 0 mean? As we defined it in this class, theta is going to be always the angle measured from the direction of the maximum stress perpendicular to the wellbore. Clockwise, it will be saying counterclockwise, but let's make it, because we did before, counterclockwise towards the other stress. So theta is going to be, we have theta 0 and theta 90. So let me do 90. This is going to be theta equal to 90 degrees. So I'm asking you to compute both sigma RR from here, from the wall of the wellbore to there, at theta equal to 0, and also in this line at theta equal to 90, where we're saying that the size of this block is actually 6 feet. 6 feet, because I'm saying that I want you to compute from the wall of the wellbore, which is 4 inches, up to 3 feet. And the first one for pressure in the wellbore 3200, and the second for pressure in the wellbore of 4000. Okay, so how do you solve this problem? You use these equations. That are right here. So if you want to right here, this value for a horizontal wellbore, and you put that long equation into it, and you will be able to calculate both sigma theta theta and sigma RR. Okay, so we do not have a lot of time to do this, but do you know what you have to do? Yes? Okay, well, let's work 5 minutes on this, and then we'll continue. Let me know if you have any question, okay? Again, if you don't have your computer right now, what I would do is take a look at these equations and start by replacing theta either for 0 or for 90. And you will see that many of these terms simplify. And remember, we just are looking for sigma RR and sigma theta theta. So just the first two equations. Okay? So replace that, the theta for 0 for 90, and you will see that that simplifies a lot. You got a question, Mr. Nolasco? Alpha, where is alpha? No, alpha, that's A. A is the radius of the wellbore, which in this case is going to be 4 inches. And R is a variable. R is going to go from 4 inches to 3 feet. That's going to be a variable. Yes, to 3 feet.
So are we going to plot like a bunch of...
Exactly. You're going to have to do like a linear space going from 4 inches to 3 feet, let's say every inch. So you'll have a nice curve that is going to allow you to plot the variation of the stresses as you go further from the wellbore.
So
yeah, you do in Excel or in MATLAB, in Python, anything you want, okay? But I want to see your homework that you actually solve this numerically, okay? I don't want just like a drawing of some lines on a piece of paper. I want to see that you actually did it.
So you want to take a picture?
Yeah.
And then put it on the...
Yeah. Yeah.
If you break that down, it gives you like an
Yeah, that's Friday. That's a lot. Yeah.
4 inches.
what is flagging you know that you're looking at.
Our varies from 4 inches to 36.
Well, cosine of 0 is just I think that's what well, so we don't
Yeah, we do have a sigma.
Oh, yeah.
You need it. Sigma minus 4 pressure gives you sigma. Oh yeah, you don't have to do it. I mean, I'll give you.
Over implied y. So we do the
to improve life. Yeah.
it's more learning about life again.
Oh yeah.
Yeah.
这个数基本的。
Have you seen Verdine? Verdine is this flashing because he can do What?
Wait, how far can
It's amazing.
you bend it?
What did you? Oh,
What?
nothing. I see.
Are you trying to look at this? So this is I was meaning that. So when you look at this one, this is sigma theta, this is sigma RR. When you look at this one now, this one is sigma theta theta, and this one is sigma RR.
I see. There's a 4-inch.
It's a 4-inch radius well.
So the bore, is this the borehole or just a
Yeah, this is a borehole. This is a wellbore.
borehole? Actually, that's only 4-inch. Oh yeah, kind of yeah.
Yeah. Small wellbore.
So 8 plus 1, we'll drag it down. You get to
Not like that?
Thank you.
All right, you're welcome.
What is this?
All right, guys. How is that going?
It's going.
Ready? Complete? The 2 parts. Yeah, you have questions?
What are we supposed to simplify equations?
To simplify with for theta equal to 0 or for theta equal to 90. So then you have just a function of R and nothing else, either for theta equal to 0 to 90. Okay? You get that? Basically here you have to plug theta, either 0 or 90. That's it. Yeah? You have a question? You have 4 equations, but I'm asking you just to solve these 2.
No, just the top 2, but like we were given 2 thetas and we were given 2 PWs.
Yes. Well, those are the 2 thetas are for the same problem, but PW 3200 and PW 4000, those are 2 different problems. Okay?
Yeah, so for the first one, then we'll have just 2 equations.
Correct. Yeah.
Because we'll have theta equal to 0 for both RR and theta theta.
Okay. So let me tell you in detail what I want. For each case, for this one, what I want is what is sigma theta theta it's going to look more or less like this, and sigma RR as a function of R for theta equal to 0, and also what is sigma theta theta and sigma RR for theta equal to 90 degrees, where this is A, 1A. That's what I want for each case. Okay, I want the numerical values of that.
For 4 lines. 1, 2, 3.
You will have 8 lines.
8 lines.
Yeah.
Oh.
So 4 for each case. Okay, all right, guys. Let's move on. In order to solve the second problem, we need to do a little bit more of work. So forget about theta for a minute, okay? Let me tell you what is going to be this equation sigma RR whenever R is equal to A. This is going to be what? 1. This is going to be what? 0. And what about this one?
Theta, 2 theta.
Whatever the value of theta is,
0.
if A is equal to R,
1 minus 1. 0.
it's going to be 0, right? Okay, so let's write that down. I'm going to move to the dog camera in a bit. This is stresses at the wellbore wall. So what you just told me is that the first equation, whenever R is equal to A, is going to be sigma RR just PW minus PP. And that's what I wrote. Okay? So that's the only term that survives. Let's go to the second one. Sigma theta theta. If A is equal to R, then this is going to be 1, right? What about this one? It's going to be 2, and this one is going to be 4, right? But notice that it's going to be 4, but we still have this cosine of theta there because we are making this for all the cases. So when you do that, then we get to sigma theta theta. Notice the sign here. Notice that we said 2, this is going to be 2 times divided by 2 is just 1. So this is just going to be sigma h max minus sigma plus sigma h min. And there in the other one we had a 4 divided by 2, so that's going to be negative 2 sigma h max minus sigma h min times the cosine of 2 theta. And these are going to be the stresses at the wall of the wellbore. Before we look at the equation, what is going to be the shear stress at the wall of the wellbore? Just try to think physically about that rather than looking at the equation. Do we have any shear stress at the wall of the wellbore? Why not, Mr. Nolasco?
Because there's no rock to shear against.
Exactly, right? There is no rock to shear against, and there is no reaction in it to apply a shear. We just have fluids in it, and fluids cannot apply significant shear unless it's just fluid shear. And if we look at the equation again, this is equal to 1. This is 1 plus 2, 3 minus 3 is just 0. So this stress is going to be 0. I'm not going to bother right now about the axial stress, so we're just going to leave it like that. Okay, so our objective now is to use these equations to tell when there is going to be tensile failure and when there is going to be shear failure. And we're going to start with the tensile failure. And what we're going to get whenever we get tensile failure in the wellbore, is something, the pressure in the wellbore is going to be called breakdown pressure, and it goes by PV. And it's a wellbore pressure, okay? So, if you remember, we said that we're going to have always tensile failure according to our definition. Let me see, where is this? Right here. We're going to have tensile failure if the maximum stress comes in this direction. The tensile failure is going to be whenever theta is equal to 0 or 180 degrees. So let's just use 0 in this case. It could also be 180, but let's just use 0. And we'll calculate what is the radial stress and the hoop stress. The radial stress is going to be the same, and actually we don't care much about that one, because the one that's going to cause tensile failure is a hoop stress. Whenever you're pulling apart the rock around the wellbore, that's when we get the tensile failure. And basically, tensile failure is going to occur whenever sigma theta theta reaches the value of the tensile strength. And notice that it's a negative, because I mean there's going to be a tension. So the only thing I'm going to do is to replace this equation into here, and we're going to get that this stress has to be equal to what we wrote over here, and what is going to be the cosine of 0. Cosine of 0 is 1, right? And so and notice that if this is 180 times 2, it will be 360, so it's going to be 1, 2, so this is going to remain the same. And what I'm going to do now is to say that use this equation to tell what is the pressure in the wellbore for which you are going to get to tensile failure. So all I'm going to do is just to put the wellbore pressure on the left hand side. Actually, we're going to call that wellbore pressure, as I told you before, the breakdown pressure. And notice that it's going to be just the summation of this plus the tensile strength. So here, for example, we're going to have notice there's going to be 3 sigma h min minus 1 sigma h max. This is going to be negative, and negative is going to be positive. So pore pressure plus this, and the tensile strength is going to go to the right hand side, and it's going to be just this equation. So this equation is telling you that the maximum pressure that you can put in the wellbore depends on the pore pressure, depends on the stress anisotropy, and also depends on the tensile strength of the rock, which makes a lot of sense, right? Because the stronger the rock, the larger is going to be the pressure that the wellbore can bear without breaking. What happens when you surpass this pressure? If the pressure in the wellbore is bigger than the breakdown pressure, then you have wellbore, what people call wellbore breakdown. But first of all, you will have a tensile fracture. And how does a tensile fracture look in the wellbore? Well, it looks very similar to this. these two are tensile fractures around the wellbore. And if we look in a little bit inside, let's see, I think what these ones are start to deviate a little bit. This one is a little bit better. So you see how it propagates from here and inside the wall of the wellbore. And you can actually also see that, let me see if we can get some light here. So there is a fracture. You can see that in wellbores too. If you do wellbore imaging, you will get to see that whenever you have tensile failure, you're going to be able to see that. Let me see. So this is breakouts. Next, tensile failure. There you have. So these are the images of wellbores, and these thin lines over here, here, and there. Those are the tensile fractures. Here, there, and also over there and there. So how far apart are these tensile fractures in angle? 180 degrees, right? Because they're opposed to each other around the wellbore. It's just because of symmetry that they are 180 degrees apart. All right, so, but you know, after all, this is very easy. The only thing that you have to do now, if you want to compute the wellbore pressure at which you're going to have tensile fractures, is just to use this equation. Yes, and that's what we're going to do right now. So for problem number let me find that. Problem number 2. I'm asking you to consider all these conditions. Here you have depth, you have stresses, and you have properties of the rock. I want you to tell me what is the breakdown pressure. Forget now about the first thing, this all this part, that's what is coming next about shear. But just tell me what will be PV for this wellbore with this parameter of overpressure with 0.52. No, first let's do it with 0.44. Okay, hydrostatic pore pressure. So let me write that down, but you already have some numbers there and you can start working, okay? I'm just gonna copy in here what you have to do. Yeah.
Where did you get the TS? Which section did you get the tensile strength equation? The tensile strength for pressure, sigma H max.
So the tensile strength is the value that you measure in the laboratory. It's something that you measure. There is no equation for it. It's just you need to go to the laboratory and measure that, similar to what you did here a couple of weeks ago. No. That's a question from Kirsch. But the value of tensile strength, this one comes from the lab. This one comes from the field. And this one also comes from the field. Okay? Yeah.
Tensile strength, was that in Brazilian testing we did?
Tensile strength, that's the value that we measured when we were doing the Brazilian test. Basically, it's the maximum tensile stress that the rock can support. So remember, it's tensile strength, maximum value of tensile stress that the rock can support. All right, so let me see. this is a place onshore, right? 7,000 feet of depth, and this is a vertical wellbore, okay? And this vertical wellbore you have stresses sigma h max. Let's do it in this direction. And sigma h mean 4,300. Yeah.
Sorry, can't see.
Let me. This is what I'm drawing. Okay. But I'm just basically copying the data from the problem into something that's nicer to look at. And we know that this rock has a tensile strength of 800 psi. That's everything you need right now. And one more thing is that we're going to solve this problem first, knowing that at this particular location lambda p, let's assume, is hydrostatic. 0.44, that's going to give you a gradient of pore pressure of 0.44 psi per foot. Okay? So I think you know how to do this. You know how to calculate effective stresses. That's all you need in your equation, right? Let me see if I can put the two of them together. You know what is the tensile strength that's given. You just have to compute the effective stresses, the pore pressure, and use the equation, and you'll get the value of the breakdown pressure. Okay? All right. So whoever gives me the answer, I'll give him or give her back some extra points.
Wait, you took away extra points?
No, I'll give you. I didn't take away extra points.
You said you'll give back.
No, I'll give you in return for your answer some extra points. Yeah.
It's 4,320 psi.
Very quick. Okay. PV, then 4,320 psi. Okay, I think that's the right value. Let's work a little bit more. If you didn't get to compute a number, try to do it and see if you get the same one. I believe that's the correct one. I'm just going to plug the. What is the pore pressure at this place?
3080.
But how much was the numerical value?
3080.
3,080 psi. And what is sigma h mean? 1220. Okay. 1,200. And what is sigma h max?
3220.
And the tensile strength is 800 psi. So this should give you this number. Okay? Everyone gets the same? So it's as easy like that. You just need to know what to calculate and how to use this data and the pore pressure data in order to calculate effective stresses. So for the homework, you're going to have to repeat this for high overpressure, for 0.52 and for 0.60. And what you're going to see is that as the pore pressure increases, your PV is going to get lower and lower. Basically, something that we're going to see later on also is that when you have higher pore pressure for the same conditions, the drilling window or the mud window gets smaller. And usually for drilling, you want your mud window to be as wide as possible because that gives you more freedom to put long casings instead of to set many casing depths. But we'll see that in later on. All right? Okay. So PV, very easy to calculate. There is just one more thing I'm going to say about this right now, and it is that here we have ignored something that sometimes is important to take into account, and it is the fact that sometimes when you're drilling, there is a, it should be a negative, I believe. There is a component which is a component of thermal stress that you need to take into account. Usually the drilling mud has a lower temperature than the formation. So if the drilling mud has a lower temperature than the formation, the drilling mud is going to cool the rock around the wellbore. And if the rock is cooling, it's going to shrink. And when it shrinks, it's going to develop tensile stresses. So this term takes into account that. Sometimes you have cases in which you may be drilling a wellbore and it's stable, no problems at all, but then you you lower a logging tool. That sometimes logging tool require lower temperature mud in order to work well, and when you lower the temperature of the wellbore, it may fail suddenly as you're doing the logging. And even though it was okay during drilling, it may fail later on if you change the temperature conditions in the wellbore.
This is the effective thermal stress. Is there something as the total thermal stress?
No. That's something that I believe that we didn't go in detail through, but it is somewhere around here in the notes where we talk about problems of thermoelasticity. And when you have problems of thermoelasticity, you can compute the effective stress by adding that thermal component. And if you want to put pore pressure and everything together, it's just you add one more term, and everything is called theory of thermoporoelasticity. But the effective stress is just one. Okay, so you need one more thing in order to solve the homework. And probably on Monday we'll still have to work a little bit more on this, on the theory, in order to get there. But we have seen that now in the wellbore, you can get to tensile failure if you increase the pressure in the wellbore enough so that it causes tensile failure around the wellbore. Well, if your pressure gets lower, you can also cause shear failure around the wellbore. And whenever that happens, we call that wellbore breakouts. And let's take the equation that we had for the wellbore before, and come on, what's going on? Okay, before we used theta equal to 0 or 180, now we're going to use theta equal to 90 or 270. And in that case, sigma theta theta is going to be this value. And what is going to be for theta equal to 90? What is going to be cosine of 2 theta? -1, right? So if this is negative, now this is going to be positive, and I'm going to have 3 sigma h max minus 1 sigma h min. Okay, so here is where it comes the, let's call it the trick in order to get it to get shear failure. In the wellbore, I have sigma theta theta, and I have sigma r, which I know it's PW minus PP. And let me do a schematic of a wellbore where this is theta, and I'm failing in shear a piece of rock over here, and this is sigma theta theta, and I have a support very similar as with the triaxial test, sigma RR on the wall of the wellbore. If this is failing in shear, which is sigma 1 and which is sigma 3? So remember that for shear failure, the equation was the maximum allowable stress sigma 1 is going to be equal to the unconfined compression strength plus sigma 3, which is the effective stress support, the least principal stress, times the coefficient that is related to friction Q. So my question is, if we want to use this equation here, which is going to be sigma 1 and which is going to be sigma 3? Sigma R is going to be will be sigma 3, right? Because that's the effective stress support on the wall of the wellbore. And sigma theta theta is going to be sigma 1 1. So all I'm going to do now is just to replace sigma 1 1 by sigma theta theta and replace sigma 3 by sigma RR, and you see that there are some terms that repeat in the equation, and basically when you equate all of this and we solve for PW, you're going to be able to get an equation that tells you that the pressure in the wellbore at which you're going to have shear failure is going to equal to the pore pressure plus 3 times sigma h max minus sigma h min minus unconfined compression strength of the rock divided 1 plus the coefficient Q. So with this equation now, you can calculate what is going to be the pressure in the wellbore for which you have shear failure. And let's try to understand a little bit this equation. What this is telling you is that the larger your stress anisotropy, the larger this pressure in the wellbore is going to be. And also that the bigger the strength of your rock, unconfined compression strength, the smaller this one is going to be. I didn't tell you before, but the breakdown pressure is going to work for us as an upper bound. What is the maximum pressure that we can have in the wellbore? While this shear failure is going to work as a lower bound. What is the minimum pressure that we can have in the wellbore? Ideally, we want to have these limits to be far apart, so we have a range or a window of mud pressure that we can work with, and our objective is to get this one as low as possible. And the stronger your rock, either because of UCS or because of Q, the lower this value is going to be. So what I like that you do later on is that you continue solving this problem and you tell me what is PW shear. And the rest of the homework is just the more of the same. Yes? Yeah.
You said there wasn't shear in the wellbore, the bottom of the wellbore.
Yes.
You said there wasn't theta, there wasn't sigma theta R at the bottom of the wellbore, but now we have shear.
I'll answer that to you. If you can come over here, I'll try to answer that. Okay? I'm not quite sure what you were meaning.